Hi everyone, my name's Kevin, and I'll be presenting a paper, Hearing Your Voice is Not Enough, an articulatory gesture-based liveness detection for voice authentication. And the author of the paper are Zhang, Tan, and Yang, and they also conducted the experiment. The background of this topic is that there has been increasing interest in using biometric recognition as an alternative method to the traditional way of using password for user authentication. And this works well because of the uniqueness of biometric characteristics like voice prints. And it also can be seamlessly integrated with smartphones. Applications such as WeChat already have it integrated, where a user can choose to log in with reading a set of number, and the system will try to authenticate if the user is real. So there are definitely some obvious challenges. The first one is with the mimicry attack, where the malicious users mimic the way that the real user speaks, and this can not only be the sound, but also the gesture as he or she speaks. And the second one is the playback attack, where the malicious user can use a pre-recorded voice from the genuine user to get past the authentication process. In order to prevent this from happening, a liveliness detection is important in order for the system to know that a real authenticated user is speaking. Here's a simplified explanation of the difference between a real user and a loudspeaker. For a real user, there are sound movement coming from the articulators, such as lips, jaw, and tongue, that are different from the one-dimensional sound coming from a loudspeaker. These movements can be recognized by analyzing the Doppler shift, which is a change in frequency caused by the reflection from the articulator, and this will be discussed further in later slides. A loudspeaker also has a relatively simple set of articulators compared to humans, and it relies more on the diaphragms to move only forward and backward to create a sound wave. And the input signal controls the frequency and intensity of the changes in air pressure to create the sounds. There have been some previous work on similar topics. So one is voice vault and ones that rely on challenge response approaches for liveliness detection. And this requires a user to repeat a set of sentences in addition to the recorded ones. And this definitely increased some burden on the user side. And there also has been a smartphone-based liveliness detection using magnetic field measurements. And this requires the users to speak while moving the smartphone in a particular trajectory that the authentication system needs. Furthermore, there's also a method using a solution that measures the time difference of arrival changes of phoneme sound to two microphones on the phone. And this requires the users to hold the phone in a specific position. It is pretty effective, but also requires some operational overhead. In this study, it introduced the system of voice gesture, which is a smartphone-based liveness detection system that is highly effective, and it does not require the user to hold the phone in any particular way. It differentiates human from loudspeaker, and it uses the phone as a Doppler radar and analyze the reflection going back to the microphone. It doesn't have the operational overhead that the other work requires. And here we'll dive into the specifics of voice gesture. Here is an overview of the system design. First, the phone emits an inaudible acoustic sound at 20 kilohertz at the beginning of the authentication process. Second, the microphone records the user voice and the reflected tone that is at a higher frequency. The system then tries to separate the human voice at below 10 kilohertz from the high frequency band at around 20 kilohertz, which can show the Doppler shift caused by the articulator's reflection. Next, the feature is computed using metrics based on frequency shift as well as observed energy distribution. Next, a similarity score is being computed, and successful authentication occurs when the score passes a certain threshold. Of course, there is a system requirement that the phone needs to be able to emit and record high-frequency sound. So let's break down the methodology. First step is to extract Doppler shift, and that's to separate human voice at below 10 kilohertz from the high-frequency band at 20 kilohertz. And it does so by converting the recorded signal using short-time Fourier transform at a window of 250 millisecond window. Then the consonant is being segmented using the automatic speech recognition tool. And then a probabilistic graph is being generated with a user pronouncing the word in all accents, and the search is being conducted using the hidden markup model to find a segmented phoneme for the words. Remember that phonemes are small units of sound such as p, b, d, that involves different movement of the articulators, and the system uses these segmented phonemes to extract the Doppler shift. So the second step of the methodology is to normalize the extracted features. And one type of feature is the energy band frequency features, and that is to partition energy capture into 6 subbands to account for the varying distance that the speakers are away from the microphone. And then a frequency contour is being constructed. The bottom graph shows the frequency contours at different STFT bin numbers, indicating velocity shift with different phonemes. Then there is this frequency band energy features, which separate the relative velocity movement of the articulators into 5 different subbands, and the average energy is being calculated at each subband. Looking at the graph on bottom right, band 5 contour has the lowest energy, most likely because it's furthest from the microphone. The next step is to remove the imperfection caused by noise by decomposing features into large scale, which is called approximation, and small scale, called detail component. Then, a dynamic threshold is set to remove noise from the detail coefficient, corresponding to sound with small values. Then, the filter detail coefficient is combined with the original approximation coefficient to construct a denoise contour that can be used as a feature to liveliness detection. The next step is to determine how similar the two sounds are, and a Pearson correlation coefficient is computed for the energy base, frequency base, and the combined features. The coefficient is used to determine the liveliness of the person and validate if the user is authentic. 21 participants from 21 to 35 years old were chosen with 10 passphrases of varying length that repeat 3 times for a register. The experiment is being conducted under replay attacks and mimicry attacks. For the replay attacks, a loudspeaker, a built-in speaker, and a Samsung earbud were all used in different trials to replay the passphrases. Then, in a mimicry attack, the participant articulatory gesture were being recorded on video, and the other participants were invited to watch the video carefully and mimic the way that the real speaker in the video articulate the passphrase. Here are some metrics to measure the success of the system. First, it's the FAR, which is the likelihood of incorrectly classifying a replay attack as a live user. Then it's a true accept rate, which is the probability of correctly detecting a live user. Then it's the ROC, which shows true accept rate versus false accept rate when the thresholds are different. And next is the false reject rate, which is the probability of mistakenly classifying a live user as a replay attack. And it's the equal error rate, which is the rate at which FAR equals FRR. And then it's the accuracy, which is the proportion of correct prediction among all evaluations. So here are the results for the experiment. On the very left set of graphs is the result for the playback attack, and you can see that the combined feature, it has the accuracy of 99.3% and the EER of 1.26%, which is the best out of all the features. And the energy-based feature also had a um, accuracy of 97.4% and an ER of 2.83, which is also pretty good. Then, looking at mimicry attack, it is also showing a similar trend of the combined feature of having a 99.3% accuracy in detections and 1.21 EER. And the frequency-based kind of feature has a accuracy of 95.9% and the ER of 4.67. So as a result, overall we can see that the combined features definitely perform the best in terms of accuracy and ER, and the energy-based features perform the second best overall, and then frequency-based feature also perform relatively well, but not as good as the other two features. Here are some more results for the experiments. As we can see that when the phone is placed in front of the mouth, it performs slightly better in terms of accuracy and EER. And this makes sense because the microphone is able to record more details from the articulators when the phone is closer to the mouth. And we also see that with higher sampling frequency, it also improves the performance in terms of accuracy and ER. And this is because the phone is able to capture more details of the articulatory gesture, which means that it's able to capture more of the Doppler shift caused by the reflection of the articulators. And overall, the experiments, the system works pretty well with different phone models. There wasn't a lot of big difference between different models, and there is only a slight increase of accuracy with the increase of passphrase length. Here's some discussion of the experiment. So in the experiment, when the attacker tried to conduct a mimicry attack, it needs some prior knowledge about how the user speaks and as well as the way that the speaker moved his or her articulators. And in the real world, the attacker might not have as much information about the real user. And in that case, at least from the experiment, it's almost 100% accuracy for detecting false user when the attacker does not have prior knowledge about the real users. So that is definitely an optimistic aspect of the system. There are definitely some limitations for this experiment, and a main one is that the demographic for age in this test is relatively young, ranging from age of 21 to 35, and it should be expanded to a more diverse age group in order to get a full understanding of how this system works. Furthermore, the system is also only evaluated for several months, and this does not account for the fact that human speaking characteristics may change over time. For example, people going through teenage age may have their voice change, and whether the system can detect that change and know that it's the same user is still a questionable aspect of the experiment. Another thing to test out is to let the participant hold the phone even closer to their mouths to see how it's able to detect when the frequency is relatively fast. In conclusion, voice gesture extract features in the Doppler shift from the articulatory gesture by using the phone as a Doppler radar. It is pretty practical to use because it only requires simple instruction and reduces the operational overhead for the user. It can achieve over 99% accuracy with an ER of just around 1%, which makes it a safe tool to use while also practical and efficient. And this concludes my presentation, and thank you for listening.